All moving objects possess momentum. Momentum is the product of mass and velocity of an object. Systems involving collisions are governed by the law of conservation of momentum. Let us take an example of a collision of two masses, a very common situation which you would have come across when playing or watching games such as marbles, billiards, snooker, and carom. A ball of mass m1 moving with a velocity v1 collides with a ball of mass m2 at rest. Immediately after the impact, the balls move with different velocities in different directions. In this section, we will learn about specific relationships between their masses, velocities, and angles of movement. Collisions in one dimension. Collisions involving objects moving along the same straight line are known as collisions in one dimension or head-on collisions. Let us consider a completely inelastic one-dimensional collision, whose animation and schematic diagram are shown here. As it is a completely inelastic collision, the two masses would move together in the same direction, that is, θ1 equals θ2 equals 0. Here, subscripts Vi and Vf stand for initial and final velocity respectively, that is, velocity before collision and velocity after collision. Here, initial velocity of mass m2 is 0. After collision, both move with the same velocity Vf. Total momentum of the two masses before collision equals m1 v1i plus m2 x0 equals m1 v1i. After momentum, both move with the same velocity Vf. Total momentum of the two masses after collision equals m1 vf plus m2 vf equals m1 plus m2 vf. By law of conservation of momentum, we get as total momentum before collision equals total momentum after collision, that is, m1 v1 equals m1 plus m2 vf. Vf equals m1 by m1 plus m2 into v1i. We number this equation as 1. Kinetic energy before collision equals half m1 v1i square. Kinetic energy after collision equals half m1 vf square plus half m2 vf square, which equals half into m1 plus m2 into vf square. The loss in kinetic energy on collision is delta K equals kinetic energy before collision minus kinetic energy after collision. Delta K equals half m1 v1i square minus half m1 plus m2 vf square equals half m1 v1i square minus half m1 plus m2 vf square equals half m1 v1i square minus half m1 square by m1 plus m2 v1i square equals half m1 v1i square into 1 minus m1 by m1 plus m2. Substituting equation 1 here, we get half m1 m2 by m1 plus m2 v1i square. Thus, in an inelastic collision, kinetic energy is lost and the quantity lost is positive. Now, let us consider an elastic collision. As it is an elastic collision, after the impact, the two masses move with different velocities in different directions, as illustrated in the diagram. But for simplicity, let us suppose that their direction remains the same, that is, θ1 equals θ2 equals 0. Here, subscripts Vi and Vf stand for initial and final velocity respectively, that is, velocity before collision and velocity after collision. Here, initial velocity of mass m2 is 0. After collision, mass m1 will move velocity v1f and mass m2 will move with velocity v2f. Total momentum of the two masses before collision equals m1 v1i plus m2 into 0 equals m1 v1i. Total momentum of the two masses after collision equals m1 v1f plus m2 v2f. By law of conservation of momentum, we get total momentum before collision equals total momentum after collision m1v1i equals m1v1f plus m2v2f. Number this equation as 1. Now, kinetic energy before collision equals half m1v1i square. Kinetic energy after collision equals half m1v1f square plus half m2v2f square. In elastic collision, kinetic energy is conserved. So total kinetic energy before collision equals total kinetic energy after collision. m1v1i square equals m1v1f square plus m2v2f square. Denote this equation as 2. Now we can rewrite equation 1 as m1v1i minus v1f equals m2v2f. m2v2f equals m1 into v1i minus v1f. We denote this equation as A. Substituting equation A in equation 2, m1v1i square equals m1v1f square plus v2f into m1 into v1i minus v1f. m1v1i square equals m1v1f square plus m1v1i v2f minus m1v1f v2f. m1v1i square minus m1v1i v2f equals m1v1f square minus m1v1f v2f. m1v1i into v1i minus v2f equals m1 v1f into v1f minus v2f. This equation can be rewritten as m1 v1i into v2f minus v1i equals m1 v1f into v2f minus v1f. v2f v1i minus v1i square equals v1f v2f minus v1f square. v2f v1i minus v1f v2f equals v1i square minus v1f square. v2f into v1i minus v1f equals v1i minus v1f into v1i plus v1f. Hence, v into 2f equals v1i plus v1f. Numbering this equation as 3, substituting equation 3 in equation 1, m1 v1i equals m1 v1f plus m2 into v1i plus v1f. m1 v1i equals m1 v1f plus m2 v1i plus m2 v1f. v1i into m1 minus m2 equals m1 plus m2 into v1f. v1i into m1 minus m2 by m2 plus m1 equals v1f. v1f equals v1i into m1 minus m2 by m1 plus m2. Denoting this equation as 4. Substituting equation 4 in equation 3, we get v2f equals v1i plus v1i into m1 minus m2 by m1 plus m2 equals v1i into 1 plus m1 minus m2 by m1 plus m2 equals v1i into m1 plus m2 plus m1 minus m2 by m1 plus m2. v2f equals 2m1 v1i by m1 plus m2. Thus the equations are v1f equals v1i into m1 minus m2 by m1 plus m2. v2f equals 2m1 v1i by m1 plus m2. Thus, by knowing the masses of the two colliding objects and the initial velocity of one of them, we can calculate the final velocities of both objects. Such calculations play a crucially important role in the automobile manufacturing industry and transportation safety. Let us see two special cases of the above system. Case 1. When the two masses are equal, when m1 equals m2, then substituting this condition in the two equations, we get v1f equals 0, v2f equals v1i. The two equations show that the first mass comes to rest and pushes the second mass so that the second mass moves with the same velocity which the first mass had before collision. Case 2. if one mass is greater than the other, example, m2 greater than m1. Here value of m1 is relatively very small as compared to m2, and so it can be neglected. Then substituting this in the two equations we get, now v1f equals minus v1i, v2f equals 0. That is, the larger mass is undisturbed and the lighter mass reverses its direction by keeping the magnitude of its speed unchanged. An example of case 2 is when a car collides with a truck. The truck comes to a halt, but the car is pushed back with the same speed it had when it approached the truck.